Hello everyone and welcome back to Nunley Math as we continue our discussion of probability. So far we've spent about 4 or 5 different lessons discussing probability, starting with the simplest of probabilities and then using counting trees and area models to help us find the probability of more complex events. We then used the multiplication counting principle to determine how many events were possible without having to draw a diagram or a area model. And then we use that to calculate the probability of multiple events occurring at the same time. So what I've done is I've gone through and I've created another lesson called independent versus dependent events, where we're going to take all that information and try and look at it in a slightly different way. So I've created a problem for you that looks like this. Let's go ahead and read through it together. So apparently it is cool in junior high to wear socks that don't match. I don't know why that is, but apparently it's a thing. To assist with making her sock selection random, Aria decides to put all her left foot socks in one drawer and all her right foot socks in another drawer. As a side note, did you know that Under Armour sometimes puts L's and R's on some of their socks? Like there's a difference. I don't know. Maybe there is a difference between a left-footed sock or a right-footed sock, and they have it customized to give you superior comfort. I don't know, but I just find it interesting. Anyway, she draws one sock out of the first drawer and then pulls out another sock from the second drawer, wearing whatever combination she gets. What is the probability that she has to wear a lime left sock and a yellow right sock? So there's two things we're looking at: the probability of wearing a lime left sock and the probability of wearing a yellow right sock. Let's look at those separately. The probability of a lime sock. I come over here to my first drawer. Notice that there are 1, 2, 3, 4, 5, 6 socks in that drawer, only one of which is lime, meaning my probability is 1 out of 6. I then look at my second drawer. These have all my right-footed socks. Notice they are the same colors as the left-footed socks because they are the matching pairs. There's still 1, 2, 3, 4, 5, 6 socks in the drawer, and only one of them happens to be yellow, meaning the probability of a yellow sock is also 1 in 6. And we learned in our last video from the multiplication counting principle that if we want to know the probability of a lime then a yellow, we just take the individual probabilities and multiply them together, because the probability of multiple events occurring simultaneously is the product of their individual probabilities. So I could go through here and I could draw a counting tree of this particular problem. Notice I've copied the probabilities that we calculated over here for you. And most of the time I would not require you to do a counting tree, but there's some things I want to look at, and the counting tree is going to help us see them better. So from my start over here on the left, I would draw a line going out to each of my left socks. Notice there are 6 left socks, so I list them all out. Notice I'm giving myself lots of room because I know this is going to take up some space. And then I realized that if I draw a lime-colored sock out of the first drawer, or for the left foot, the sock that's on the right foot could be any of these 6 colors drawn from the second drawer. And then if my left sock is salmon, then I can draw any of them. If my left sock is blue, I can draw any, and so on. What's important to realize is no matter what sock I pick out of the left drawer, it has no influence or control over what I draw out of the second drawer. And then on the end, I'm going to list all the outcomes that I was able to come up with. Notice there are 6 lime, 6 salmon, 6 blue, 6 orange, 6 yellow, and 6 red. Altogether, that is 36 different options. And out of those 36 different options, lime and yellow only occurs one time. Hence, our probability 1 in 36. I want us to look at this just a little bit differently for a moment. Suppose that Aria leaves her right sock drawer open and her dog eats all of her right foot socks. She must now wear 2 left-footed socks to school. If she blindly draws out 2 socks one at a time from the left sock drawer, what is the probability that she will get a lime sock first and a yellow sock second? So we're changing the story now. Instead of having drawer 1 and drawer 2, she's going to be drawing from drawer 1 and from drawer 1 again. drawing twice from the exact same drawer. Now that's going to change a couple things for us. So when I go to look at my probability, I have to keep in mind that if I'm drawing from the same drawer, if I draw a lime sock first, there's no longer a lime sock in the drawer. There's only one of each, which means it is impossible for her to draw lime and lime. The same thing happens down here if she draws a salmon sock first, because now she still has a lime sock in the drawer, but she no longer has a salmon sock in the drawer. It's impossible for her to get salmon, salmon. Same thing here. It's impossible for her to get blue and blue because once she's drawn out the blue sock, she's changed what's still in the drawer. Same thing with orange, orange. Same thing with yellow, yellow. Same thing with red, red. We have changed what's in the drawer between the first draw and the second. Now, when I look at the probability of getting the lime sock on the first draw, let me erase my ink here real quick. The probability of getting the lime sock is still the same. There are still 6 socks in the drawer. There's still only one of them that's lime. So the probability of the lime sock is the same. But the probability of the yellow sock is different. And that's where we really need to slow down and think about this. Because when she goes to make her second draw, if you look here, only one of the 5 remaining are yellow. Down here, only one of the 5 remaining are yellow. Only one of the 5 remaining are yellow. Only one of the 5 remaining are yellow. Down here, there are none of the 5 remaining that are yellow. And down here, there's one of the 5 remaining that are yellow. Now, what that means is if we look through here, there's 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. No matter what she drew the first time, she's going to have 5 choices left for her second draw, which means the probability of a yellow is 1 out of 5. Only 1/5 of those are going to be yellows, which means the probability of a lime followed by a yellow, that's this choice here, is 1 out of the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Did I miss one? 5, 10, 15, 20, 25, 30. That's what I thought. It's 1 out of 30. I missed one of those as I was counting down. 1 out of 30. And notice that our multiplication counting principle still holds. If I take the probability of the lime sock and multiply it by the probability of the yellow sock, I get the probability of both socks. The difference here being when you're drawing from the same drawer. When you draw from the same drawer, what happens in your second draw is affected by what happened in your first draw. The probability here changes because the first event has an influence or a direct connection to what happens in the second event. This is called a dependent event. Dependent event. And I think I have that defined on the next slide. The first event was independent because what happened to the first draw here, when I pulled a sock out of the first drawer, it didn't affect or influence what was in the second drawer. Down here, it's dependent because what happened in the first drawer affects the second draw. So let's take a look at the definitions of these two terms. Events are independent when the outcome of the first event does not affect the outcome of the second. They are dependent when the outcome of the first event does affect the outcome of the second. Now, it's going to be important for us anytime we have more than one event occurring that we're clear on whether we are dealing with something that is independent or dependent. So let's take a look here. A bag of jelly beans has 5 black, 4 white, 2 green, 3 blue, and 6 yellow beans in it. Vicky reaches into the bag, pulls out a jelly bean, then puts it back. She then reaches in, pulls out a second jelly bean, and eats it. What is the probability that the first jelly bean is black and the second jelly bean is yellow? Well, the first thing we need to know is how many jelly beans are there altogether? 5 black, 4 white, 2 green, 3 blue, and 6 yellow, for a total of 20 beans. Once we know there are 20 beans, we have to ask ourselves, does the first bean that I draw affect what's available for my second draw? And there's a phrase in here that's going to help us with that. It says, Vicky reaches into the bag, pulls out a jelly bean, and it says, but she puts it back. As soon as we're told that she puts it back, we know that the 20 total beans that were there at the beginning are still there for the second draw. That's going to make this independent events. So when I say the probability of a black bean followed by a yellow bean, I'm going to say, what's the probability that my first draw is a black jelly bean? Well, there's 5 of those out of the 20 altogether, so my probability is 5 out of 20. The probability of getting a yellow bean on my second draw. There are 6 yellow beans. The 20 that I started with are still there. That's a total of, or a probability of 6 out of 20. We can multiply those together. The probability of getting a black bean first and a yellow bean second is 30 out of 400. In my class, my students would not be allowed to leave it that way. They would have to simplify that to 3/40ths. I might ask them to convert that to a decimal or percent as well, but that's not really what we're talking about here today. Not too bad, right? Especially when the first outcome does not affect the second. Independent events are the easier of the two to work with. Now, some of you might be looking here and be noticing that these fractions are not in simplest form, and you might be wondering, can I write that as 1/4 times 3/10? Absolutely, you may. And when you're done, you'll still end up with 3/40ths. The difference is, instead of simplifying here at the end, you've just simplified at the beginning. Most people find it easier to simplify at the beginning because then you get smaller numbers to work with. Let's try another one, shall we? A bag of jelly beans has 5 black, 4 white, 2 green, 3 blue, and 6 yellow beans in it. Notice this is the exact same thing we had over here, which means we still have a total of 20 jelly beans. Vicky reaches into the bag, pulls out a jelly bean, and eats it. Now this is where the problem gets interesting. In the previous problem, it says she puts the first bean back. In the second problem, she pulls it out and eats it. That tells us that this is going to be dependent events. Dependent events, because as soon as she eats that bean, it says she reaches in and pulls out a second bean and eats it too. There are fewer beans in the bag for the second draw, just like there were fewer socks in the sock problem and she was drawing out from the same drawer. This says, what is the probability that she will draw a black bean first and a yellow bean second? So the two problems are very similar. We're still looking for the same probabilities, but in this case, the second draw is going to have a result that is influenced by what happened in the first draw. So let's walk through this. The probability of drawing a black jelly bean is still 5 out of 20. There are 5 black beans, there are 20 beans altogether. The probability of drawing a yellow. Well, there are still 6 yellow jelly beans in the bag, but there are no longer 20 beans in the bag because we just ate one. If we ate a bean, there are now 19 beans in the bag, meaning the probability is 6 out of 19 that we will get a yellow. Notice before it was 6 out of 20. The dependent events have caused the second denominator to be different. And just like before, we would multiply that together and simplify. A few of you may have noticed that 5 out of 20 is not in simplest form. You can make that into 1/4. Also notice that once you've simplified to 5/20ths, you can actually simplify diagonally as well. You've got a 6 on top and a 4 on bottom. That would simplify and become 3/2. and then you multiply those together and you get 338 much more quickly. Again, a lot of people find it easier to simplify at the beginning because you have smaller numbers to work with. Does that all make sense? Let's do another one, shall we? Independent, where the first event does not affect the second. Dependent, where the first event does affect the second. Jacob is playing a game that's similar to Scrabble. He reaches into a bag that contains all 26 letters of the alphabet, with each letter appearing only once on the tiles. He pulls out 2 tiles, one at a time. Is this an example of independent or dependent? And what is the probability he will pull out 2 vowels? Well, let's take a look. It says he pulls out 2 tiles, one at a time. There's nothing in here to indicate that he puts the first tile back before drawing the second. That tells us that these events are dependent. And we already know there's 26 tiles altogether. So let's set this up. The probability of a vowel followed by a vowel. Well, let's see. The first vowel, what are the vowels? A, E, I, O, and U. 5 of the 26 letters in the alphabet are considered to be vowels. You could sometimes say sometimes Y and W, but for the sake of this problem, we're not going to deal with Y and W as vowels, just the traditional 5 vowels. But when he goes to do his second draw, the number of vowels has changed. He drew out a vowel here, meaning there are less vowels to draw out here. Instead of having 5 vowels, there are now only 4 vowels. There's 4 vowels, and there are no longer 26 letters altogether. There are now only 25 letters. Now, a lot of people say, well, what if the first draw was not a vowel? If the first draw was not a vowel, this 5 out of 26, that would be an example of one of the other 20 choices. So we're only looking at if the first one was a vowel, what's the probability the second would also be a vowel? So it's 4 out of 25. Again, multiplying those together and then simplifying, you get 2 out of 65. Some of you may have noticed that 5 out of 26 does not simplify and 4 out of 25 does not simplify. But if you look diagonally, 5 and 25 will simplify, 4 and 26 will simplify. The 5 and 25 would become 1 and 5. The 26 and the 4 would become 13 and 2. And when you multiply those together, you get 2 out of 65. Again, I don't care which of these ways you do it. A lot of people find it harder to have to simplify large numbers than to simplify at the beginning. One last problem. At a picnic, your friend reaches into an ice-filled cooler containing 8 regular soft drinks and 5 diet drinks. Your friend removes the can but then decides that he's not really thirsty and he puts it back. That phrase right there, he puts the first can back, is very important because it tells us these events are independent. They will not affect each other. What is the probability that your friend and the next person to reach into the cooler both randomly select a regular soft drink? All right, we're looking at the probability of regular soft drink followed by a regular soft drink. We know there are 13 drinks altogether because there are 5 diet and 8 regular. So the probability of the first regular drink, 8 out of 13. 8 are regular out of the 13 total. Times, since he puts it back, the second draw still has 8 regular drinks out of 13, making your solution 64 out of 169. As I look at this, I can see there's nothing here that will cross simplify, so that is the only way I could solve this problem. Again, my students would have to have this in simplest form. I might make them turn them to fractions or decimals, so they need to make sure they read the directions very, very carefully. That's all we've got for today. Hopefully that made perfect sense to you. Again, the trick is to make sure you know before you start working on the problem whether it's independent or dependent. And then number 2, to keep an eye on that second draw, that second event, because that's the one that always ends up being affected. I wish you all the very best of luck. Thank you for watching us here today. Make sure you like and subscribe and turn on your notifications, ring that bell, and all those other fancy YouTube buzzwords. We do wish you all the very, very best of luck. You all take care of yourselves, all right? Bye-bye.